With this lesson, we're going to begin to tie in more closely everything that we did with all of those convergence tests and the nth term test for divergence, along with our power series. So it's going to begin to make a little more sense why we needed to know all of this. And we're right here at the very end of our lesson, so we'll tie everything in together. I'll give you a little theory background here. It's not something that you really need to put in your notes. I just want you to kind of see where this is going. So the fundamental importance of a power series is that we can take an impossibly difficult function, even a non-elementary function, and we can use their approximating polynomials that are infinite, their power series in other words, to manipulate that mathematically to within a very certain degree of accuracy. We can take an impossibly hard function to deal with and turn it into a polynomial with infinitely many terms, and very near the point around which we built the polynomial, we know that the power series is going to act just like the function. So it's really important that there's only one power series that represents the function that we're trying to emulate. And that's where this whole idea of the uniqueness theorem comes in. Again, this doesn't need to be in your notes. I just want to convince you that it is true that there is only one power series near that center point of x equal a that is going to act like the function f of x in question. And this should make it clear why we know that that power series is going to be unique, because from the output of the function to how many ever derivatives we want to take, we are guaranteed that the polynomial that we're building, the power series, is based on having the same attributes for those coefficients that the function does. So the function can't have more than one power series in x minus a that represents it, because the function is the driving force behind what the power series looks like. So just so you know, there is one and only one power series that emulates a function, and therefore we can talk about, like we did in the last lessons, that function being the sum of the power series. So it's also extremely important, and we already know this. This is something we already know, so again, it doesn't have to be in your notes, but I want to formally give it to you here so that what we do next with these power series, I've kind of built a theoretic basis for, so you'll go there with me. So also of extreme importance when using an infinite power series to represent a function, we need to know for what values of x the series acts exactly like the function. Now, we've always said it was on some interval very near the point over which we built the power series. It's why we spent so much time determining convergence for infinite series in the first part of our series work. So for each unique value of x, this series is a series of constants that we can test for convergence when we have a value of x in this series. Then all of these terms are real number values. It's a series of constants, and we can test to see if that converges or diverges. Now, converges for what? Well, does this x value that we put into this power series, does it act just like the function at that x value? That's what convergence means. Or does it not act like the function at that x value? That's what divergence means. So notice that a power series is a function of x. These series involve variables, but they still behave like series. Everything that we learned about series in N, all of those tests, the nth term test for divergence, p-series, the integral test, the limit comparison test, the direct comparison test, all of those still apply when x is involved. So a power series may converge for some values of x and diverge for other values of x. It depends on the values of x we put into the series. And for our series work on the AP test, finding the values of x for which our power series converges is a big part of what we do. So this lesson begins to tie everything in together. All right? So here's the interval that we're talking about. There's some value r that is a distance from A, whether it is to the right of A or whether it is to the left of A. There is an interval over which those x values will cause the series to converge and act just like the function. Act just like the function meaning have the same outputs as the power series will have the same outputs as the function. So the series to converge to act like the function. And this interval is a big part of the work that we're asked to do on the AP test. So again, we know all this. We know about the error. The error is the next term in the series. We have been interested in finding that interval when we talked about the Lagrange error bound, and you'll recognize that as the Lagrange error bound. So here is what we're going to be doing when we talk about convergence of a power series. There is two things that we're asked to find. One is the radius of convergence, and it says that for series centered at 0, this is important because it looks different for series centered at A. The convergence for power series, a sub n of x to the n, a power series in x, is always an interval of one of the following three types. We're either going to have that series converge and act just like the function at only x equals 0. That's what number 1 says. The interval is the single point x equals 0. Or some interval from negative r to r. And it might include the endpoints. That's why I have put less than or equal. Or it might not include the endpoints. Or it might include only one of the endpoints. And then the third value of x, for which we could have a radius of convergence, where our power series acts just like our function, is for the entire real number line. So when we're asked to find the radius of convergence, we're going to have three types of answers depending on what's going on. If the series acts like the function only at x equals 0, this is what is going to be the result from number 1, then our radius of convergence is 0. From number 2, if there is an interval, x would be less than or equal to the absolute value of r, then that gives us a radius of convergence of r. So that follows from number 2. And following from number 3, if we converge for all values of x, then our radius of convergence is infinity. I know this looks and sounds confusing like everything else we've done in series. It's really straightforward in practice. There's not going to be any guesswork when we actually get down to doing this and finding the radius of convergence. So let's do that. How do we find the radius of convergence? How do we find those values, either x equals 0 or x equals some interval r, or x equal the whole real number line? Well, it turns out that the process is we are always going to run the absolute ratio test. And we're going to find rho. We know a series, whether it's got x in it or not, converges, and that's what we're after, is convergent values. A series converges when rho is less than 1. So what we're after is we're going to run that absolute ratio test of a sub n plus 1 over a sub n and we're going to get rho. And we know that if we set rho less than 1, then this is where the series converges. And here's what's going to happen for us. What happened for us before when we just had series in n is that rho wound up some real number. Now rho is going to wind up some manipulation on x. And if we take that manipulation on x and set it less than 1, then we can find the interval or the radius of convergence. So that's what we're fixing to do. Let's work this specific example, and you'll see in practice it's a lot easier than it is in theory. So a sub n, just like we did before, is x to the n over n factorial. A sub n plus 1. The only difference here now is that we have x involved. We are now dealing with power series as opposed to just the other series we had been dealing with before. Now, we are not taking x to infinity. Please notice that. We're still taking n to infinity. As far as n is concerned, x is a constant. So we are going to have x to the n times x. Notice what I'm doing here, same thing I did before, over n plus 1 times n factorial, multiplied by the reciprocal of a sub n. That's absolutely no different than what we did, let's say, if we had 3 to the n over n factorial. Now I'm just doing what I did with 3. I'm doing it with x. No different. But remember, as far as n is concerned, x is some constant. So we're going to clean this up algebraically. That's gone, that's gone, that's gone. And so now we have a limit as n approaches infinity of the absolute value of x over n plus 1. As n approaches infinity, this is some constant value, remember, as far as n is concerned, some constant value over huge. This is going to tiny, and there's our rho. And we know we converge for any rho value less than 1. So this is a convergent power series. But for what values of x? Is there an x value that I can put into this limit where this thing doesn't converge? Any x value from negative infinity to positive infinity. Find an x value that I can put into this limit where I won't get 0 for an answer. There isn't one. I can put any x value in here I want to put. This is the third case that we were looking for over here. The radius of convergence, this thing converges for every single value of x we could possibly put in it. Another way to look at it is rho doesn't involve x. So, let's put this down here. So, x has no bearing on this series convergence. And since x has no bearing on whether it converges or not, it converges for any value of x we want to put in there. The radius of convergence is going to be infinity. So the radius of convergence is infinity, all x values. There isn't a single x value that we can put into this series where it doesn't converge.